Hi, I need to adjust the screen. There we go. At any rate, this is a chapter 17, kind of some lecture and examples on things. Again, a lot of this is really for cohort A since you haven't been here, but I think it's going to be assigned to both. So this deals with wave optics, diffraction, and thin film interference. I think it really is important to make sure that we talk about some of these things explicitly, right, and give you some examples. So the beginning of, and all of this deals with constructive and destructive interference. So constructive interference happens when waves line up in such a way that you get crests and crests, which gives us a little crest and a little crest, gives us a bigger crest. Trough and trough gives us a bigger trough. So we get a larger wave, a larger amount of energy at that point in time. It's the principle behind resonance with sound waves and some of the factors we see here with diffraction and things like that. Destructive interference is when we would have crests and troughs interact. If you have a crest and a trough, at the same time, if they interact with each other, you get no energy pulse at all for that instant in time. So this is when waves build up with each other, or parts of waves do that, and this is when they cancel out. We're going to see that effect with diffraction quite a bit. So a couple of the formulas, and these are the formulas that I have had up before and listed. They're in the wave part of our AP Physics 2 formula sheet. 1 and 2 are mentioned here pretty early in chapter 17. This is a general wave equation. Velocity of a wave in meters per second is the traditional. Frequency of a wave is in hertz, which is basically or things per second with no unit on top. And wavelength is in meters. This deals with relating the index of refraction, which is n, sometimes called optical density, to the speed of light in a vacuum, that is c, divided by the velocity in a new substance. So the idea is, as the minimal value for this would be 1, so that means something would be going the same speed as in a vacuum, and air is like 1.002, I think. And as this ratio goes up, this can't change. Speed in light in a vacuum is constant, but the speed in different substances goes down. So same value divided by a smaller number gives us a bigger number over here. And that just tells us the ratio of those speeds. And it also affects how things refract, which is discussed in chapter 18. This is the general formula we're going to use for things which involve diffraction. It is used for almost everything and almost all types of diffraction. There are different versions of it, a number of different versions in your book, a number of ways they look at different angles, like sine of an angle, tangent of an angle, stuff like that. Stick with this because it's general and we can apply it in all those situations and it's less to remember. Okay, so we'll come to that in a minute. So basically what diffraction is if we have pulses of waves, and let's say we're looking at crests of waves here, and let's say they're all moving to the right. If we have something that's got an opening, a small opening, like this, when the wave hits that, we know if this opening is about the same size or on the same size as these wavelengths, then the light is going to diffract around that as it passes out. So what's going to happen here is we'll see wave fronts that are like this. And your chapter talks about things called Huygens Principle, which is why that happens. I'm a little less interested in that, although you probably should know it, than to see this particular pattern. So we see things spreading out like that. And that's true as long as the opening, again, is about the same size as the wavelength. It could be up to 10 times bigger, 10 times smaller. We still see that effect. We don't see much effect when this is much bigger or much smaller than a wavelength. So for wavelengths of light, they're very short. So a lot of times we'll have light, which we'll say is visible light to us, is between 400 in 700 nanometers. Short wavelength is violet light, long wavelength is red light. Well, a nanometer is 10 to the negative 9th meters, so that would be 4.0 times 10 to the negative 7th meters to 7.0 times 10 to the negative 7th meters. So for light to diffract, it's got to be really small openings or slits. If we have more than one opening, we see a particular pattern occur. And a diffraction grating is something with many, many openings. In this chapter, they talk about openings like diffraction patterns with one opening, two openings, or diffraction grating where we have many openings. The nice thing about that is those all really can be used to look at, we can look at this formula to think about it. So what will happen is if we have some openings with wave interference, we're going to end up getting a pattern of waves which fall along the screen where we could see, and we're going to see areas of constructive and destructive interference. I do want to let you know what these variables stand for, though, before I stop this part of the video and get to the next part. So this is going to be the distance between openings on a diffraction grating, or distance between slits. And a lot of times this is given in millimeters or centimeters or things like that. We need to have it in meters to make sure everything's standard. Or if we only have a single opening, this is the width of a single slit. It results in the same effect. Okay? And that's because, of course, as I erase this here, if light diffracts, so let's say again we've got waves coming this way, if we have a single opening like that, light diffracting, around this and this can interfere with each other. So we're going to think about that if we think about single slit opening. So that's what the D means. Distance between slits or width of a single slit. I'll get to the sine theta in a minute. M is something known as an order number. It is a whole or half number usually, but it represents the path length difference in wavelengths. So that's why it's multiplied by wavelength over here. So, for example, if we have something where we have m equals 1, that means we've got two rays of light or waves of light with a path difference of 1 wavelength. If we have one full wavelength path difference, that means the one that's behind or longer by a wavelength, we could think of that, it's by exactly one wavelength, we would get constructive interference because a crest from the one wave, fantastic, would meet up with a crest of another wave. If we have a path length difference of 0.5, or an order number of 0.5, path difference of 0.5 wavelengths, half a wavelength difference. So that means every time one of the waves has a crest, the other would have a trough. So when we have things that are whole numbers for M, we have constructive interference. That means we get the light, if we're talking about light, reinforcing itself, so we get a brighter color of light. If we have a path length difference of 0.5, we have destructive interference. and we tend to have a dark spot, a spot where the light is canceled out. So there's several different examples about this that are talked about in your chapter, but this is the big idea. What about if you have something with m equals 0? Well, then it says that both waves travel the same length, so there's no path difference. That also means we would have constructive interference. It's a whole number, and so a crest from one wave would get there at the same time as a crest of another wave. So that's kind of what we're interested in. The angle I'm going to have to show you with what's happening next, and that's the next part of the video. So big ideas. This chapter relates to constructive and destructive interference and making some predictions about that. These two formulas are things we've talked about a little bit already. This is a diffraction formula that is good for any type of diffraction, well, almost any type, but it's the one we're going to think about. Single slit opening, double slit opening, or diffraction grating, which has many openings. And that's pretty good. All right, this is part 2 of the Chapter 17 Demonstrations Examples video, which deal with wave optics, diffraction, and thin film interference. This diagram, not to scale. How do I know that? Well, I'm trying to show this as being a laser, and it's shooting red laser light through a diffraction with grating where we're looking at 2 openings. And then that light's going to pass over here and hit a screen. Okay. The key thing with this particular thing with diffraction is that we need to be able to make mathematical predictions using this formula that was mentioned earlier. I need to have monochromatic light. What does that mean? It means it's one wavelength of light. And so that would be something like we would use, it would be like a laser. We have a source of mercury light that we use for a lab, hopefully, people are here. But I have lasers as well, which can be used for that. Well, why is that important? Well, because if we have all different wavelengths of light, many different wavelengths here, we're going to see that it's going to diffract at many different angles. Okay, and so we have something like this. This is a pair of diffraction glasses. I think I showed you examples of that before. But if I walk around here, see white light, and I put this over the lens of the computer camera, you're probably going to see things look kind of weird. I'm not sure if that's going to work out well or not. It should look rainbowy, may or may not work. Okay. At any rate, I tried to draw this as monochromatic light with crest, trough, crest, and so forth. But I can't do those over here with what I need to do and keep them aligned. I am not that good an artist, as I'm sure all of you know by now. So I'm going to draw this light as a straight line as it passes through here. Now, when it comes through this opening, we know that the light spreads out according to Huygens Principle. So it goes into these sort of spherical shells. But those light rays are going to interact with each other. In other words, the light coming through here and through here will interact. I'm only going to draw a few of those types of rays. I'm going to do one particular example. So this is a midline that's meant to be halfway between those. So if I draw a straight line here, and I look at this, I could have light going to the center of this screen as one of the possible paths. I did that horribly. This is going to be bad. Okay, so if these 2 slits are the same distance apart from this midline, and they reach here at the midline, there is no path length difference between those 2 waves. In other words, I don't know how many waves this is, or wavelengths. So this is super magnified. It's ridiculous because waves are on the order of 10 to the negative 7th meters. But let's say this top one traveled 4,372 wavelengths. That means this bottom one also traveled 4,372 wavelengths. And since this is monochromatic light, that means when we have it strike here, if a crest from this one is striking, a crest from this one will strike. A trough from this one is striking, a trough from this one will strike. So that means you're always going to get constructive interference. So what we would find here is a central maximum or a bright dot. Actually, it probably wouldn't look like a dot, it would just be a bright spot on that screen. So something like that. So I'm going to erase this and erase this. Now, light rays from each of these are going to be interacting with each other all along the screen, but they're going to be acting completely constructively the whole time because there's going to be a path length difference in terms of the number of waves. If it's not completely constructive or completely destructive, we're not going to think about it. But at some point up here, we're going to have a spot. I'll make it a little darker right there, where we have light from this one and light from this one reaching that spot. And again, they should be at the exact same spot. I didn't draw that very well. At this point, this particular very special spot up here, we're going to have destructive interference. What that means is the light from this bottom slit is going to travel half a wavelength more than the light from the top slit. Always, because of the geometry with those angles. So if a crest comes from this one, you have a trough from this one. If a trough comes from this one, you'll be having a crest from this one. If something at a certain point of a wave comes from this that's not a crest or trough, whatever comes here will be the exact opposite, 1/2 cycle off. So let's say in this particular case that this one travels for 4,897.5 wavelengths. This one would have to travel further because it's coming from below, so this would be 4,898 wavelengths. Whatever the case may be, they're going to completely cancel each other out, and we're going to see a dark spot up here. That is half a wavelength difference. Back in this formula, we would put the m, or the order number, as 0.5. So I'll leave that as a dark dot over there, but again, I'm going to erase this for my next example. So if we go further, and by the way, we would have another one down here, the same distance away. So we see a symmetry both above and below. As we go further and further, the difference in path length is going to increase. In other words, if we go up here or down, one of the waves is going to have to travel even more than a half wavelength different in path than another one. In fact, let's say we have an area up here. We would have another one down here, where we have this wave coming like so, this wave coming like so. I drew those better. So at this point, they don't travel the same path length as they did here. So we don't have m equals 0. What we do have is we've got this one traveling a full wavelength more than this one. So again, I don't care what the exact numbers are. Let's say that this one is, I don't know, 4,000. And if I could remember the numbers from before, I would. I'm bad at that. So again, these are dummy numbers. They're only for comparison to each other, not between the different examples. So I'll make this one very different. Let's say this one's 375 wavelengths, and this one would be 376 wavelengths. My path length difference is 1 wavelength, and I would get constructive interference from that. Same reasons that I've said before. Down here, I would get constructive interference. So you're going to have a whole series of light and dark spots. That is a diffraction pattern. Now eventually, it's going to go so far if you don't have a huge screen where it'll never hit the screen. It'll bend a certain amount. So usually we think of a central maximum, these minimums, and maximums over there. So on that screen, we would think of this as corresponding to m equals 0, m equals plus 1/2, I'll put 0.5, m equals plus 1, m equals negative 0.5, m equals negative 1.0. So again, a series of bright and dark spots, basically due to constructive and destructive interference. Well, how does this relate to the math over there? The way it relates to the math is we can predict or calculate some things based on what we know. So oftentimes, all we can particularly measure is we might know the wavelength and we might know these geometrical distances. And we could use that to find the distance between these diffraction gratings. Or you might be told, hey, here's a diffraction grating with some information about it. That would give us this d, or this distance in between. So this is d right there. And we might be asked to figure out what wavelength the light is. So something like that. So let's do the example up here. See how we can figure that out. So let's say I'm looking at this particular spot. I'm not going to draw those waves again. I had them out earlier. If I draw a line from the center of this to the center of that bright red spot, I should do that in a different color for dramatic effect. That doesn't look anything like a straight line. It's a little bit better. Then what I can do is I can see that I've got a triangle here. So on this screen, you should be able to use a meter stick or something to measure this distance, which I'm calling delta x. That would be the same as across here. You should be able to know the difference between the central maximum to see that and this first order maximum is what it's called. I'm going to call that delta y. Well, that can help us figure out the angle. So I can't figure it out directly using sine of an angle, but I can using tangent, because tangent of an angle is equal to opposite side over adjacent side. So that's going to equal delta y over delta x. So if I want to figure out what that angle is, then you take the inverse tangent, delta y over delta x. That'll get me my angle, and now I can plug that back into the sine theta. Now, for those of you who are mathematically astute, you might realize that for small angles, sine of the angle and tangent of the angle are going to be very close numbers. So your chapter or your book talks about small angle approximations and how you can use a different formula for that. I don't want you to use a different formula for that. This is the one, that way we only have one to think about. So we'll get the angle using tangent or inverse tangent, put that in here, and then we're going to take the sine of that particular angle. So if we know this, we know this is 1, we can figure out the wavelength of our light. And by the way, notice the pattern here. As this distance decreases, as the slits get farther to get closer together, this is going to be set, like we're going to call this 1 the whole time if we're looking at the first bright spot. The wavelength from this laser isn't going to change. So if this gets smaller, then the angle gets bigger. If this gets bigger distance between them, then the angles get smaller. So the pattern you see kind of fans in or out depending on these particular things. So that's something that's good to think about, that type of mathematical relationship. And that's the end of part 2. I think we need a magic word. I think the magic word should be Valentine. Okay, with this third video, we're going to be getting into thin film interference and just the big ideas of that. The last part of the video, I'm going to do a single example, and hopefully you pay attention to that. But there's one thing I forgot to put up on the diffraction part of the video, and that is this. So we said that with this d sine theta equals m lambda, which is our general formula here. This d is the distance between slits. And if you know that, that can help you out. But a lot of times, what happens is you aren't directly given that information. What you're told is the number of slits per unit of distance. Say, this diffraction grating has 10,000 slits per centimeter, or 500 per millimeter, or things like that. And we've got to figure out this distance in between. So let me just go through and show you how those, also fantastic, are related. So let's say this pair of glasses, rainbow glasses, has an N of 2,000 slits per, let's say, centimeter. So the first thing I'm going to do before I do a conversion to get this is I'm going to make sure it's slits per meter, because I want to keep it in standard units. So that is equal to, there's 100 centimeters in a meter, so that's 2,000 times 100. So that is 200,000 slits per 1 meter. Well, how do I figure out this then, the distance between the slits? It is the reciprocal of this. So N is equal to 1 over D. D is equal to 1 over N. So if I put 200,000 in my calculator and I flip it, I should be able to get my answer, which I think I know how to do. I think it's going to be a 5, but the problem is I'm going to get the number wrong, like the number of decimals and so forth. So I have that, and I get 0.000005. So D is 0.000005 meters between each slit. I probably should say that as 5.0 times 10 to the negative, so the decimals there are 1, 2, 3, 4, 5, 6. So that is what I would put in for the D in D sine theta equals m lambda. So in labs that we do, we're going to have to do that as well, but I just want to give you a heads up. Again, not on your formula sheet. Okay, so we're done with diffraction, this part. The next part, and this is, again, I think a really challenging concept, it's called thin film interference. I've seen this in some parts of free response questions and some multiple choice questions before. So big ideas behind that. We see a bright color or brightness with constructive interference. Just like we've talked about before, darkness is destructive interference. Most of these questions I've seen have been asking about bright spots or constructive interference. Big ideas also is when we have a path length difference, is a whole number that's constructive, right? Path difference is a half number that is destructive interference. So kind of important. The other thing, other big ideas we need to think about is what we're really thinking about is light that is reflecting off of surfaces, two different surfaces. So we really have two layers, or two different interfaces, three different layers of material. So let's say this is air. We've got water floating top of oil. So three materials, air, water, and oil, two interfaces between air and water and oil. We're going to think about light coming down and reflecting off of both of these surfaces, because at most surfaces, light partially reflects off and partially refracts through. So the other big ideas, so those are a few over there, is light reflecting off a more dense, more optically dense, so it's a greater N number, has a phase shift of 180 degrees or half of a wave, has a 1/2 wavelength phase shift. And I'll call that a flip. I don't think the AP or College Board would call that a flip. Last part to go along with this, light reflecting off a less optically dense material does not flip. Does not undergo phase shift. Well, that's going to be important because it's going to have to let us know how the reflected light is going to interfere with each other. Oftentimes, what we're asked to do is think about what would be a minimum thickness of a material that would give us, say, this constructive interference for a certain wavelength or color. So, oftentimes we're asked about the thickness. And usually it's minimal thickness. Because it could be half wavelengths longer than whatever we get with that. So let me give a quick example that's conceptual, and then the last part of the video will be a numerical example. I don't know why I erased that. Oh well, sorry, hopefully you can pause. So let's say I have green light. And let's say that that is a wavelength. Oh, it's St. Patty's Day is coming up, so we can think about that. Wavelength is, let's say, 532 nanometers. So I think that's true for a type of laser. So I'm not going to draw it as waves. I'm going to draw it as just a straight line. So let's say we have light that's incident upon a surface, so it's coming in like this, and it hits this surface. Some of it's going to reflect back off, and some of it's going to go down here to this next surface. So the question is, would this light have a phase shift, or would it flip? Well, we're coming from air, but we're reflecting off of water, which is more optically dense. So that would flip. So I'm going to say flip. That lets me know that I've had a phase shift. So for the light that continues through here, now it's in water, but it's reflecting off of oil. And the question is, will that undergo a phase shift? Well, it will, because in this case, oil is more optically dense than water. So it will undergo a flip when it happens to reflect off of here. Flip. So something like that. So they've both flipped. So what that means is, if this was zero thickness, if we did a pretend experiment and this was zero thickness, then these would be constructively interfering with each other because they're both flipped, they both have a half wavelength phase shift, and therefore a crest from this would be parallel or lined up with a crest from the first one. Okay, so that kind of makes sense. Well, let's say we want to find out the minimum thickness of this. Well, what we've got is we've got light coming down and coming back up. So if I think about that, I've got a path length of this longer wave length, or this longer beam of light, is going an extra thickness of this, plus, and it comes back up, also a thickness. So essentially, that distance, twice the thickness, of this thin film would have to equal 1 full wavelength for us to get constructive interference. Why is that? Well, we know we only get constructive interference when we have a full wavelength of path difference where something is completely aligned, like a crest and a crest or a trough and a trough. So when this was 0 thickness, they'd be aligned since they both flipped. So this part of the ray that goes down to the very bottom here and all the way back up, for it to line up again, it's going to need to be 1 whole wavelength longer. That's the minimum it could be. Now we could also have different thicknesses of 2 and 3 and 4 wavelengths longer, but normally we're interested in the minimum thickness here. So that means the thickness of this thing is going to be 1/2 of a wavelength. Okay. And I could figure out what that would be mathematically. Now there's a little bit of a sneakiness with that. You might say 1/2 a wavelength, and you might say, oh, 532 divided by 2, that would be 266 nanometers thick. That would seem like it'd be reasonable. But if we go back to these things from early in the chapter, these formulas over here, we know that as we go into things that are more optically dense, the speed of light slows down. So this goes down, that's the speed of light, in the new substance. The frequency does not change ever when it goes into a new substance, so that is still equal. That means the wavelength also would go down, it would get shorter. So if the wavelength in water is shorter than the wavelength in air, that means our thickness of water, while still 1/2 of a wavelength, wouldn't be 1/2 of 532, it would be 1/2 of something smaller. So I could figure out what that is by taking 532 and dividing by 1.33, and that's 399. So I'd say wavelength nu over wavelength is equal to, actually, speed of light nu over speed of light here. So it's kind of flip-flop. So basically the way I can do that is I can say this is equal to my original wavelength divided by n. So that's 532 over 1.33. So my new wavelength actually is 399 nanometers. So in this case, this thickness, 1/2 of a wavelength, would be 1/2 of 399, which is about 200 nanometers thick, not the 266 that we thought it would be before. Oftentimes they'll only ask you this conceptually. You wouldn't have to do the math. They might ask you in terms of wavelengths, which is 1/2 a wavelength, so they probably won't do that. The last part about this is you might say, well, wait a minute. I get this first light just reflects off equal angle out as angle in, but wouldn't this refract and bend to something more vertical if it's going into the water or to the liquid? And you're right, it would, but I've never seen that asked or thought about in terms of AP physics questions. If you're really doing something with optics, you need to think about that. But yeah, these are things like why oil that's floating on like a little puddle will look, all those colors are like green and blue and orange and things like that. It's thin film interference. It's why bubbles have a thin film interference. So I'm going to get rid of this for just a second and finish off by changing something about this example really quick. Now let's say this is a bubble, and in fact, we've got just a layer of soapy water. So let's say this is back at air again. 1.00. So if it's air, well, I've got this one's reflecting off the water. It's still going to flip because this index of refraction at the interface is higher than this. But now this one, reflecting off of this air, it's reflecting off something that is lower index of refraction. So the light ray will not flip. No flip. flipping. And it does not have a phase shift. So what does that mean now? Well, it means that these are if this thickness was 0, this would be 1/2 wavelength off of this. And that means that we would have destructive interference. So in order to get back and have constructive interference, where we have full wavelength path length differences, we need essentially this total path down and up to equal 1/2 of a wavelength. So I could say something like the thickness, which is down plus up for that path, so that's 2t, I need to be 1/2 a wavelength. So what that means is now the minimum thickness I would need for constructive interference would be 1/4 of a wavelength. And if we said that the green light was like 399 nanometers, that means this thickness now would need to be only 1/4 of that, or about 100 nanometers. So the only thing that changes is because this one doesn't flip, we end up getting the path length difference that we need is only 1/2 a wavelength, and that's why this changes. So we could have things happen where both rays flip, both rays don't flip, one does and one doesn't. Rather than try to memorize a bunch of formulas for that, the big idea is to draw this out. I like this arrow down and arrow up showing the path that the light ray of this longer ray will take. That's a lot. So thanks. Last part of this Edpuzzle video. Thanks for hanging in there if you've hung in there. Again, something we normally would have time to do in class. It would be more interactive in class also. So I'm going to do an example with thin film interference, a numerical example, and I want to find the minimum thickness for constructive interference for a red laser where the wavelength is 640 nanometers in air, or you could say that that would be in a vacuum. These are the principles that I talked about before. Also something to remember in terms of the fact that the wavelength can change as it goes into something that's optically different. So drawing this, the first thing I want to do is think about whether or not the two light rays that are reflecting are going to flip or not flip. Are they going to have a phase shift? So if we have something like this coming in, we've got red light here. This is more optically dense than air, so this will have a flip or a phase shift. So I'm going to say flip right there. The next thing, this part of this ray is going to go through the bottom, and it's going to end up hitting this surface. So it's coming from a substance that's got an index of refraction of 1.33, about reflecting off of something that's an index of refraction of only 1.00, so that will not flip. Not flip. And by the way, the principle behind whether these flip or not is pretty interesting. Conceptually, if you remember when we had the slinky out and we were shaking it back and forth, we noticed that if I sent a pulse down the slinky and it was on someone's right side and they were holding their arm firm, then the slinky would reflect off it to the left side. And that was due to Newton's third law of slinky pulling on hand to left, hand pulling on slinky to the right, or vice versa. I might have got my directions mixed up, but the idea is they're opposite. So the reflected pulse off of something solid was always going to be the opposite direction. So that's kind of what's happening here when you think of it reflecting off something more optically dense. If it's not reflecting off something more optically dense, it's acting like a wave that would just be continuing. So it would continue in phase or not flipping. So if I have something like this, then I could think of this path length difference as going down through the thickness and coming back up through the thickness. So that's this part of the ray and that part of the ray. So that is two thicknesses of distance that's different. So the path is 2t. Well, what do I need that path length difference to be in order for one of the rays that didn't flip and the other one that did flip to constructively interfere? I need that to be a half wavelength. In other words, if this distance down plus up is exactly a half wavelength more than this, and this didn't flip, then it'll be 1/2 wavelength. So then the thickness of this thin film would be 1/4 wavelength. So if I plug these numbers in and I say, okay, the wavelength of a red laser is 640 nanometers over 4, that's 160 nanometers. And the only thing you would have forgotten is that the wavelength of light in the material goes down. So in fact, what I've got to do is I've got to say my new wavelength, and actually if they only asked it in terms of wavelengths, it would be something like that. (640 nanometers) or 1.33. It's probably going to give us a weird number. It didn't. I should. Well, so the new wavelength, should have known that, 480 nanometers. So what I actually would do, say, this should be over the new wavelength, which is 480 divided by 4. That's going to be 120 nanometers of thickness, or 1.2 times 10 to the -7th meters. So that's how you would go about solving that. We won't have too many of those, but I really want you to understand it conceptually. So take a look at this. If you need to pause the video at this point, you can do that. I'm going to erase this and put one last thing up. And that's that on page 600 of your book, they have two formulas that you can use if you can memorize them for which cases to use a certain formula to find constructive interference or destructive interference. So these are on page 600. So one of the formulas is 2t, or twice the thickness, is equal to m, that's the order number, or path length difference in terms of wavelengths, divided by n. And that's the index of refraction. The other one is 2t equals m plus 1/2 lambda, I should have done that better, over n. So basically it's either this m or m plus 1/2. So my gut instinct is probably what we're looking here is almost always in my mind this m is going to be 1 because we're looking for the shortest path length difference, the thinnest film. And this would be when we have one of the waves flip and the other one doesn't, and this would be when we either have both waves flip or neither wave flip. So that might be the way to write that down. At any rate, I think that'll help. But again, I can't remember those, and it's not on your formula sheet, so you won't have it during the AP exam. Thanks. Have a great day. And, oh, do we need another magic word? How about lollipop? That'd be a good word, lollipop.